For this final learning module of Chapter 2, we'll be introducing the dot product. You've probably seen the dot product before in previous classes. Just remember that it's one of two or three, depending upon how you look at it, multiplication type operations that you can apply to vectors. And the unique thing about the dot product is if I take two vectors and compute their dot product, I get a scalar, which is why the dot product is often referred to as the scalar product. Similar to a lot of things in this course, there's two different definitions that I can use to define the dot product. One is more geometrical based and one is kind of more linear algebra based. On the geometrical side of things, if I have any two vectors, naturally they define a plane and are separated by some angle theta. And here we'll kind of uniquely define theta as the smallest angle between these two vectors. Note I can also always define an additional angle that would sum to 360. However, if I always choose the smallest of the two, I know that theta will be restricted between 0 and 180 degrees. So that's kind of like my geometrical definition. And in addition, I have the more convenient linear algebra-based definition where I can compute a dot product. It's just the sum of the common components of the two vectors. So one of the primary applications of the dot product is it kind of allows you to measure similarity between a vector and another vector. And you'll see that concept throughout the remainder of your engineering coursework. And if you decide to go on to graduate school, you'll see it after that. So here we're going to look at how that property can be exploited in order to define the projection of a vector onto a given axis. Or another way to say that is the component of a vector along a particular axis. So one of the unique things about the dot product is if I have a unit vector along any axis and I take a dot product with a vector, I get the component along that axis. So naturally, you know how this would work if u sub a was I hat, j hat, or k hat. Going back to this previous formula, just think about if one of the two vectors was I hat or j hat or k hat. Of these three terms in the sum, 2 would always be 0 under that scenario. However, this unit vector doesn't have to be along the traditional coordinate axes. I can use this for any line of interest. So fortunately, based upon the last learning module, we have the ability to compute a unit vector in any direction as long as we can kind of define a position vector. So one other thing I wanted to say is this decomposing A into a component along this axis is also referred to as projecting A along to this axis. And you can kind of see why that is when we look at this kind of right triangle approach. If I drop a perpendicular from the tip of A to the axis of interest, naturally that will form a right triangle. And much as we've seen so far in the course through using our trigonometric ratios, so COTOA, this side length, which coincides with the axis of interest, is given by the product of the magnitude times the cosine of this interior angle. So oftentimes for applications, when you decompose a vector along a coordinate axis, you'll also be interested in the orthogonal component. And the way which we can always find the orthogonal component to that axis is to exploit the basic triangle rule of vector addition. Namely, when I decompose a vector onto an axis, say u, the sum of that decomposition with a vector perpendicular is always my original vector, regardless of how the axes are kind of rotated in a two-dimensional plane. So I can compute the perpendicular vector, or I should say the component along the perpendicular axis, as the difference of the original vector and that projection onto axis u. So let's actually look at an example problem here. We have a hook, we have a force acting upon it, and it's described by its components in rectangular form in 3 dimensions. We're interested in finding this angle theta, which is the planar angle between the line of action of the force and this line segment going from point A in the geometry to the origin, denoted by O, along with the projection of this force along an axis defined by that line segment, AO. So if we think about the solution steps, obviously we know that this is in the dot product section of the course, so it's probably going to involve a dot product. But if you think about it, if we just had a way to write an expression for a vector along the line from A to O, we could take the dot product of any vector along that line with this force vector. And we know that this angle theta is given in terms of the geometrical definition of the dot product. Mag vector 1, mag vector 2, cosine theta. So if we, not knowing theta, of course, if we compute that, we'll have one unknown on that side, but we can relate it to the linear algebra-based definition that we have for the dot product on the other side and solve for theta. And in terms of the projection we just spoke of, if I want to project a force onto an axis, all I need is a unit vector along that axis. So hopefully you see both of those things are going to require an initial step of determining a position vector from A to the origin. And as we spoke of in the last learning module, in order to determine a position vector from A to the origin, I start by specifying the coordinates of both. I'll do the origin first based upon the way that they've drawn the coordinate system. The origin is just at point 0, 0, 0. In order to determine the coordinates of point A, notice that along the x direction to go to A, I need to come out 1 unit along the positive x-axis. Along the y-axis, I'm moving in the negative direction, 2 units. And then along the z-axis, I'm moving up 2 units. So the coordinates of that would be positive 1 in x, negative 2 in y, and positive 2 in z. Remember that in order to define a position vector from A to the origin, that will be denoted as RA0, I take the difference of the coordinates of O with the coordinates of A. So one thing to be careful of when you do this is, since the y coordinate of A is negative, you're going to have a minus and negative, which will become positive. When you do that, hopefully you get a position vector of -1, 2, -2. You can sanity check it and ask yourself, to go from A to the origin, do I move in the negative x direction? Well, negative x direction means I need to go back into the page, and yes, I do. Do I move in the positive y direction? Well, yeah, that means I need to move to the right, kind of in the plane of the screen. And do I move in the negative z direction? Well, yeah, that means in the plane of the screen that I have to go down. So I can compute the magnitude of that position vector by taking the square root of the sum of the squares. Know that whether these components are negative or positive, when you square them, you get a positive result. The book was kind and gave us a perfect square for that result. That length, or distance between A and 0, is 3 meters. We also will need to, later on down the road, not immediately, compute the magnitude of the force vector, which we do the same way, only difference being that here, first, you don't have a perfect square, and the units of these two quantities will be different because one is describing length or position, the other is describing force. Once we have these two, we'll compute the dot product between the two vectors, kind of using the linear algebra-based approach, which means I'm going to take my position vector that I calculated and my force vector, which I was given, and I'm going to multiply the like components and add them. So just for an example, on the x components, x component of the force was -6, multiplied by the x component of the position vector was -1. Negative times a negative gives me a positive 6. I'm going to repeat that 3 times, sum the results, and get a scalar as expected, which will have units of kilonewtons times meter. Once I have kind of the linear algebra expression for the dot product, I want to go back and use the geometrical expression because it involves a quantity that I want to solve for, which is this planar angle theta. So recall that another way to write the dot product between two vectors is the magnitude product times cosine of that angle. I can isolate the cosine of that angle as the ratio of the dot product, which I computed via linear algebra here, divided by the product of the magnitudes, which I computed in step 2. You'll notice that once I do that, I actually get a unitless quantity, which isn't overly surprising because it's going to be a equivalent to the ratio of side lengths, right? Because this is a cosine of theta. So I can solve for theta by taking an inverse cosine, and if you do that and round to 3 sig figs, you'll get 57.7 degrees. So that was the first part of the problem. Second part of the problem, I want to project this force onto this axis. Since I already know the magnitude, I computed it on the last slide. All I need is a unit vector along this axis, and this should say from A to O. I'll correct that before I post. Ignore it for the time being. Magnitude of the force, not rounded, was root 126 kilonewtons. We have RAO from the previous slide. We have the magnitude of that position vector from the previous slide. Notice that that cancels the units of meters and just gives me units of force. That's why when I work these by hand a lot of times, you can kind of get lazy with your units, but don't get too lazy. And if you scale this normalized vector by this magnitude and do your math, you'll get about 6 kilonewtons for the magnitude of that force. So hopefully that was a good refresher for dot products for you, and hopefully chapter 2 was a little bit of a refresher overall. That will conclude chapter 2, and we'll move on to chapter 3.